Okay, so good afternoon, Alpha. Today we're going to discuss about the flow path immersed object, the second part. But before we start further to talk about the calculation and also the concept, I want you to check out on the video in YouTube that you may see that the link you may see in the next slide. Okay, so later you can check out the video on YouTube, and this is the link. Yeah, don't forget to watch this because this is important for you to know the basic concept of the fluidization bed. Okay. Nah, in the subchapter, in the second part of fluid path immersed object, we will discuss about the behavior of the fluidized solid particles and the fluid passes it. So if yesterday we talked about the fluid passes the immersed object and the immersed object is in the static position, in this part we are talking about the fluid passes the immersed object, but this immersed object do not statically stays in the same place, ya. So it is fluidized, ya. Jadi dia akan bersifat seperti liquid, ya. Dia bergerak juga. Oke. Yang kemarin kan immersed objectnya stay in the same place, ya. That's why it is called as a fixed bed or packed bed, ya. But in this part, of the chapter, we will talk about the fluidized solid particle. Yeah, so the solid particle that is immersed inside the fluid, it will be fluidized. Yeah. Okay, so it has the behavior similar to the fluid. Okay. So the outline, the outline includes the concept of fluidized bed, the minimum velocity and particulate for particulate fluidization, the pressure drop and minimum fluidizing velocity, expansion of the fluidized bed, and minimum bubbling velocity. Okay, so we go first to the concept of fluidized bed. Yeah. So the fluidized bed, happens when the packing materials starts to fluidize or start to have a behavior like a fluid. Yeah, and usually the fluidization of the solid particles depends on the velocity of the fluid passes them. Yeah, so we can see from the figure below. Yeah, so first we have a fixed bed. Yeah, so in this condition of fixed bed, the particle of the packing material is not move. Yeah, does not move. Okay. So it stays at the same place. Yeah, however, this type of fixed bed is not very stable. Loh, why, Miss? Yeah, because usually for a fixed bed, they will have some materials that is stacked up above the packing material to maintain the position of the packing material. So it will not move. Yeah, however, as you can see here, this fixed bed do not have anything stacked up above. Yeah. So when the fluid coming in from the bottom with a higher velocity, it will start to move the packing material to become, starting to behave like a fluid, starting to move. Yeah. Okay. So as you can see here, from the left to the right, the fixed bed has the lowest fluid velocity and has the lowest particle distance. Yeah, however, in the most right figure, it has the highest fluid velocity and the highest particle distance. Yeah, so at first, when the flow of the gas or liquid is very slow, it will not change the position of the packing material. So that's why we can say it's a fixed bed. However, as I said previously, it's not stable because there is no material stacked up yang ditumpuk di atas ini Sehingga jika kecepatan fluid, ya gas atau liquid dari bawah ini semakin cepat, packing materialnya akan mulai bergerak. Ya, it will start to move. Ya. Nah, so when the higher velocity is introduced, as you can see, yeah, the particle, yeah, start to fluidize. Yeah. Okay. Nah, the first time the packing material start to fluidize, yeah, we call it as a minimum fluidization. So the first time the packing material start to move, yeah, start to expand, yeah, we call it as a minimum fluidization. Okay. And then when we make the gas or liquid we make the gas or liquid moves in a faster velocity, then it will start to expand more. Yeah. So as you can see here, the height here is very low. Yeah, and then it starts to increase and increase. Yeah. Okay. Nah, we call this a smooth fluidization. Yeah. So for smooth fluidization, yeah, when the gas or liquid velocity increases, yeah, the bed continues to expand and remains homogeneous. So there is no bubble still, yeah, in this smooth fluidization. So the particle distance, yeah, the particle distance between every particle stays the same. Yeah, that's the smooth fluidization. Yeah, and it is one of the type for fluidization. Okay, and then we have the bubbling fluidization. Yeah, now this happens when the gas is introduced at a higher velocity as compared to the smooth fluidization. So this slow, very slow, and then this one a little bit faster, yeah, and then a little bit faster, and then it again a little bit faster. Yeah. So what happens after smooth fluidization is bubbling fluidization, because the gas passes in a quite high velocity, then the bubble, yeah, or void, yeah, we call it as a void because bubble do not have any components inside, yeah. It will grow along the bed, yeah. So we can say that the density is not the same for all region. Let's say the region which have a bubble, a big bubble here, and the region where it has a small bubble here. Of course, it will not have the same density. Yeah. While for smooth fluidizations, since the particle distance are similar, yeah, in all part of the bed, yeah. So the density in all parts of the bed will stay the same. Yeah. Okay, so that's for bubbling fluidization. And then slugging. Yeah, there is also one type of fluidization we call as slugging. Yeah, so slugging happens when the bubble, yeah, which start to form in bubbling fluidization, yeah, coalesced, ya, jadi bertubrukan satu dengan lainnya and form a bigger bubble, yeah, which fill almost the entire cross-sectional area of the bed. So as you can see here, yeah, the bubble here, yeah, and the bubble here, yeah, which one has a larger size? This one, yeah. As you can see, it has a higher size of bubble, yeah, and it almost filling in almost all the entire cross-sectional area of the bed. Okay, yeah. So if it's only fill like 1/3 of the cross-sectional area, and this one like around 1/10, ya 1/10 dari area. But this, as you can see, and this, yeah, it fills almost all of the cross-sectional area. Okay, so it's slugging, yeah, and it happens when the gas flow is getting higher. as compared to the bubbling fluidization. Okay. Yeah. Okay, so I will not go to pneumatic transport because we will not discuss about pneumatic transport here. Okay. Now, so here, yeah, we will. I will give you, yeah, I will give you a real image, yeah, of smooth fluidization, and then bubbling fluidization and slugging fluidization. So this is the smooth fluidization, yeah. So as you can see, when the gas is passes through the fluidized bed, yeah, as you can see here, yeah, the distance, yeah, between the particles are quite similar, yeah. Okay, yeah. However, for the bubbling fluidization, yeah, as you can see, there is a bubble, yeah, there is a bubble formed during the fluidization of the solid material. So there is a solid material here, yeah, looks like a sand, yeah. Okay, so there is bubble, yeah. So of course, it will not, if we magnify this graph, it will not give you the same magnification like this. If you see this, yeah, the particle distance are quite similar to each other, yeah, but this, of course not, yeah. The one with the bigger bubble, yeah, will have a smaller amount of solid particle. The one with smaller bubble will have higher particle concentration in the same volume, yeah. Now, and then this one is for slugging, yeah. So as you can see, there is a gas coming in from the bottom to the top, yeah. And then you can see, yeah, you see here, yeah, the bubble is very big, so that it fills all this, it fills all the cross-sectional area of the pipe, yeah, here. So this is slugging. Okay, now, so now before you answer the question that I will give you, so please read carefully subchapter 3.1 D1 in John Goplis, yeah. And if you have read it, then I have one question. Yeah, which fluidization provides the highest contact area between solid and liquid? Is it the smooth fluidization, or is it the bubble, or is it the slugging? Yeah. So which fluidization provides the highest contact area between the solid and fluid? Okay. Yeah. So the answer is the smooth fluidization. Yeah. Smooth fluidization will provide you a higher contact area between the solid and the fluid. Yeah. Why? Because in the smooth fluidization, the particle distance is the same in all region. Yeah, so as you can see, the particle distance are similar to each other. Yeah, and the fluid, yeah, passes not in a bulky bubble, but passes in between the individual particles. Yeah, so as you can see, in between the particle distance, yeah, there is a fluid there. Yeah. So the fluid passes in between the individual particle, not in a bulky bubble. Yeah, so it will promote the intimate contact between every particle with the fluid. Okay. Any questions up until this part? If you have any questions, please write down the comments, yeah, below, or you may directly chat me. Okay, now we're going to discuss about the minimum velocity that can make the packing materials change condition from fixed bed into fluidized bed. Yeah, and also we will talk about the porosity for particulate fluidization or smooth fluidization. Okay, now, so when the fluid flow, wait a minute, why it cannot come out? Okay, now, So when the fluid flow upward, yeah, if the velocity, yeah, that is coming in from the bottom, yeah, if the velocity of the gas that is coming in from the bottom is very slow, the solid particle, yeah, in this tank, yeah, will remain stationary, yeah, or it will stay as a packed or fixed bed. Yeah, now as the velocity of the fluid increases, yeah, the delta P of the fluid, yeah, or the upward force by the fluid also increases. Yeah, the delta P will increase, yeah, as the velocity of fluid increased. Yeah, now when the upward force by the fluid, yeah, which can be expressed as delta P times the cross-sectional area of the bed, equals to the gravitational force of the solid particles minus the buoyant force, the particle will start to move as a whole. Yeah. So when the upward force, yeah, that is exerted by the fluid, yeah, equals to gravitational force of the solid particle minus the buoyant force, yeah, now the particle will start to move as a whole, and this condition we call it as a minimum fluidization. Let me try to use the pen. Okay, so I will repeat again. When the upward force by the fluid, yeah, which can be expressed as delta P times cross-sectional area of the bed, equals to the gravitational force of the particle, because the particle have a mass. So of course it will have a gravity force, yeah, minus the buoyant force. Okay. Now, buoyant force is the opposing force of the particle weight in fluid. Yeah, so if we have a particle, they have the gravitational force, but they also have the buoyant force. Yeah. Okay. So gravitational force minus buoyant force equals to the upward force by the fluid. If it's equal, if those three are equal, yeah, so the particles start to move as a whole, and that condition we call it as minimum fluidization. Yeah, and that velocity, yeah, the velocity required, yeah, the velocity required to create a minimum fluidization. Yeah, so the velocity that is required, yeah, to create a force, yeah, that is equal to the gravitational force minus buoyant force, yeah, we call it as VMF accent, yeah, or superficial velocity at minimum fluidization, yeah. Oh, sorry. Yeah, okay. So VMF accent, yeah, V accent we know from the yesterday class, it's superficial velocity. Yeah. So superficial velocity is before it passes the immersed bodies. Yeah. So when it passes the empty section of the tank. Yeah. And MF stands for minimum fluidization. So VMF accent is the superficial velocity for minimum fluidization. Okay. Nah. Okay. And then we have another term. Yeah. We call it as epsilon MF. Yeah. So epsilon, we know, yeah, from yesterday's class, it's the void fraction. Okay. The void fraction or the empty space. Yeah. So when it starts to move as a whole like this, there should be a void fraction. Yeah. So there should be an empty spaces in between the particles, right? Now, so the void fraction at minimum fluidization is called minimum porosity for fluidization, or epsilon MF. Yeah, so this. Okay. Yeah, so the empty spaces here, yeah, the empty spaces here, yeah, at the minimum fluidization, right? So the empty spaces at the minimum fluidization, we call it as epsilon mf. Okay. Okay. Yeah, I hope you still remember the term because it's just yesterday, right? Yeah. But if not, you can open the previous subchapter. Okay, for fixed bed. Yeah, we also know the epsilon. Okay. Nah. Okay. Now again, yeah. Oh, wait a minute. Now, before I go to the smooth fluidization, bubbling and slugging, yeah. Now, again, another term is height of the bed at minimum fluidization, yeah. So the height of the bed, yeah, the minimum height of the bed, yeah, at minimum fluidization, we call it as LMF. Length at minimum fluidization, ya. Jadi ketinggian dari fluidized bed, ya, ketinggian dari fluidized bed pada kondisi minimum fluidization itu disebut sebagai LMF. Okay. Nah, okay, so after the minimum fluidization happens, yeah, as the velocity increase, yeah, as it gets increasing, yeah, the velocity, yeah, the delta P will remain constant as the bed continue to expand. So from fixed bed to minimum fluidization, there will be a delta P. Yeah. Okay. Nah, from minimum fluidization to smooth fluidization, there will be also a delta P. However, when it is fully fluidized, yeah, so smooth fluidization means that all of the particle has fluidized fully, there is no delta P anymore. Yeah, so the delta P will remain constant. Yeah, so there is no change in delta P. I mean, yeah, the delta P is still there, but there is no change in delta P. Yeah, so from fixed bed to minimum fluidizations, there is a change in delta P. Okay, from minimum fluidizations to smooth fluidizations, there is also a change in delta P. However, since in the smooth fluidizations, all of the particle has already fully fluidized, there is no more change in delta P. Yeah, and also there is no change in delta P in bubbling, slugging, and humid transport. Okay. Nah. Okay. So, yeah, the relation between the bed height or L1, yeah, and the porosity epsilon in the bed, yeah, having a uniform cross-sectional area, yeah, can be seen in equations 3.129 and 3.130. Okay, so let me try to open. Nah. Okay, yeah. So the correlation, yeah, the correlation between the length of the bed or the height of the bed with the void fraction in the bed, yeah, can be expressed as this equations, yeah, and it can be rearranged to form like this, yeah. Okay, and it can be arranged, yeah, to form an equations like this. Okay. Okay. Nah, I will go back. Yeah. Whoops, let me see. Oh, okay. Nah. Okay. Nah, and then if you want to calculate, yeah, actually this is one equations that is not written in the Janko list, but based from the example 3.16a, point A later, Yeah, you may use this formula. Yeah, L times A. L is the height of the bed. Okay, so if I have a bed like this, yeah, and it has a bed like this, yeah, L of the bed times surface area, cross-sectional area of the bed is times 1 minus void fraction. Yeah, so if you know, void fraction is the epsilon is the empty space in between the particles, right? So 1 minus epsilon is the solid particle itself. Yeah, okay. So L times A, height of the bed, times cross-sectional of the bed, times the solid fraction, yeah, is actually equals, yeah, to the total volume of solid, yeah, as if they existed as one piece, yeah, pejal, yeah, so no void at all. Okay, yeah. So, okay, yeah, if you want to be clear, to be more clear, yeah, so L times cross-sectional area, yeah, we got the volume of the cylinder, right? The volume of the fluidized bed, okay? But in a box cylindrical shape, okay? Nah, and then since we multiply it with 1 minus epsilon, yeah, which is the solid fraction, so times solid fraction, yeah, times solid fraction, sorry. Nah, volume of cylindrical times solid fractions. So of course we will get the volume of solid. Yeah. Volume of solid without any void. Yeah, because I only multiply it with the solid fraction. Yeah, so this is a volume of solid as if they existed as one single piece. Yeah. Okay. So actually you can use this LA times 1 minus epsilon to find the total volume of solid. Yeah, as if they existed as one piece atau pecah. Yeah. Okay. Nah, this is the one that I told you before. Yeah, that the pressure drop, yeah, at the minimum fluidization can be derived with this concept. Yeah. So the upward force, yeah. Well, let me change it to laser pointer. So the upward force, yeah, or we can say it's the delta P of the fluid times the cross-sectional area of the bed equals to the gravitational force of the solid particles, which is mass times gravity, minus the buoyant force. Yeah. Buoyant force is the opposite force of the solid mass weight. Okay. So it can be derived using the equation of 3131 and 3132. Yeah. Okay, so this. Yeah. Oh, let me change. Is it already? I hope so. Okay, nah, this, yeah. 3131 and 3132. Okay. Okay. Yeah, so delta P times A is the upward force by the fluid, right? LMF times A times 1 minus EMF. Yeah, that means it's the volume of the solid. Yeah, volume of the solid times the density of the particle. That means the mass of the particle, right? Mass of particle times g is the gravitational constant, right? Nah, and then, but there is still minus density here, miss. Yes, that's buoyant force, yeah? LMF times A times 1 minus epsilon MF is again volume of the particle, right? Okay. Now, when we want to move a specific volume of water by adding a liquid, by adding a solid. I'm sorry. When we want to move some amount of water by adding a solid, the volume of the liquid that is moved is the same as the volume of the solid that is added into the system. So let me draw it for you. Okay, so I have a water full like this, and then I want to move some water, right, by adding a rock. Let's say it's a stone or rock. So when I put a rock, with the volume of 1 centimeter, 1 cubic centimeter, so of course the water that is removed from the system is also 1 centimeter, 1 cubic centimeter. If I add a bigger rock, with a volume of 10 cubic centimeter, I put it here. So of course the water that is coming out from the system is also 10 centimeter cubic, 10 cubic centimeter. Nah, so actually it's the same, So it's the volume of the solid, right? The volume of the solid, The volume of the solid, is this value LMF times A times 1 minus epsilon MF, right? But I need to change, I want to change it to mass, I need to multiply it with the density of the liquid, not the solid. No, why, miss? Okay, let me go back to this graph. Let me go back to this graph. Okay, now if I have a rock, with this volume, okay, and it goes into the system, the water that is removed is also 1 cubic centimeter. But of course, the mass of the rock, that is coming into the system, if they have the same volume, as the liquid, will the liquid have the same mass as well with the solid? Jadi maksud saya kayak gini, pada saat Anda memasukkan batu dengan volume 1 cubic centimeter, air yang Anda keluarkan dari sistem itu sebenarnya juga 1 cubic centimeter. Akan tetapi, dengan adanya perbedaan densitas, densitasnya batu itu tidak sama dengan densitasnya air. Otomatis massa batu yang masuk dalam sistem tidak sama dengan massa air yang keluar dari sistem. Volumenya sama, tapi massanya tidak sama. Okay. So I repeat again. So when you want to put a rock, with the volume of 1 cubic centimeter, the water that is coming out also 1 cubic centimeter. But since the density between the rock and also the water is not the same, so of course I cannot say that the mass of the water is equal with the mass of the rock. So that's why for the buoyant force, or for the liquid mass that is coming out from the system, I will multiply the volume of the solid with the density of the liquid. Okay, times G. That's the buoyant force. And after some rearrangement, it becomes like this. Okay. Then next, Oh, why it cannot change? Let me check. Okay, since the particle in, And the second point, yeah, since the particle in fluidized bed can be in a regular shape or irregular shape, yeah, we'll change the term of diameter particle or dp with tau sdp. Yeah, you still remember, right? This is the sphericity coefficient. Yeah, since we don't know, right, whether it's spherical or it's cylindrical or it's irregular in shape, yeah, we don't know. Yeah, so we will change the dp by tau sdp. Okay, so we can see that the equations, general equations for delta p is written in equations 3.133. Okay, so I will change again. Slide. Oh, sorry. This, yeah. So if you still remember this, it's actually similar to what we have learned in Tech, right? Yeah. Okay, so it's actually similar, yeah, to the one in Tech, right? Now, however, yeah, to calculate the minimum velocity of the minimum fluidization, yeah, V MF accent, epsilon MF, LMF, then we can change the V accent with the V MF accent. Yeah, we can change the epsilon with the epsilon MF. Yeah, okay. And we can change this L becomes LMF. Yeah. Okay, so after some changes, yeah, then we can find this equation. Yeah. Okay. Okay, so after we change this, we combine these two, yeah, it's also delta P equal over LMF. This is delta P over L, but I change this to LMF, right? Because it's at minimum fluidization, right? This is for packed bed, right? This is for minimum fluidization. Well, I can combine these two, yeah, but I need to change this to LMF. This becomes VMFXN. This becomes epsilon MF. So it becomes like this, yeah, after some mathematical arrangement. Okay. 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 So I will go back again to the PowerPoint. Okay. So this already, yeah. So after we get the 3.133, yeah, it's actually for packed bed. Yeah, but since it's in a minimum fluidization condition, so I will change all of the V accent, E, L become LMF, V, MF accent, and epsilon MF. Yeah. Okay. Now, and then the Reynolds number for the minimum fluidization of the given solid, yeah, we call it as a Reynolds number, MF. Yeah, so a lot of Reynolds number. Yeah, so Reynolds number that is commonly used for fluid flow. Yeah, Reynolds number for packed bed, Reynolds number for minimum fluidization, and Reynolds number for particle. Yeah. Okay. So for the Reynolds number can be calculated using 3.135. This is for the condition of minimum fluidization of the given solid. Yeah. Okay. So I will go again back to the general list. Yeah. So this is the Reynolds number for the minimum fluidization. This is the Reynolds number for the particle, yeah. It's not for the fluid. Yeah. Okay. Now, and then after I combine the equations 3.134, yeah, with this, yeah. So I I combine these two equations, 3,134 and 3,135. After I combine these two, then I can get this equation, 3,136. Okay. Now, when the NREMF, when the Reynolds number at minimum fluidization is less than 20, so if the result of this is less than 20, which is usually it's for small particles, so the first term can be dropped from the equation. So what's left is only the second and the third. However, if the results of this is higher than 1000, so usually it's for the large particle, then the second term drops out. So what's left is only the first and the third term. And then sometimes, we also do not know the value of epsilon MF, and also we do not know the value of tau S. Miss, then what should we do? If we do not know epsilon MF and we do not know tau S. Because actually in this equation, of 3.136, we have to know the value of epsilon MF and tau S. But if we do not know, then what should we do? Wen and Yu found a variety of system. So they said that tau S times the epsilon MF to the power of 3 pretty much equal to 1/14. So actually I can change this to become 1/14. Now, while they also said that 1 minus epsilon MF over tau S squared times epsilon MF to the power of 3 pretty much equal to 11. So actually I can change this. I can change this into 11. So finally, after combining this value with these equations, then I can get this 3.138. Okay, and after some rearrangement, then I can get these equations. Okay. Now, these equations of NREMF, so this equation of NREMF, it actually holds only for a Reynolds number range of 0.001 to 4000. So if it's less than 0.001 of it, or if it's higher than 4000, we cannot use these equations. We have to use these equations only. Okay. For these equations, it can hold any number, but for this equation, it can hold for 0.001 to 4000. Because Wen and Yu found a variety of system of this, these two value only in those Reynolds number range, 0.001 up until 4000 only. Okay. Any questions up until this part? Okay, so if not, then we will go to the example 3.16. Okay, so we go to the example 3.61. So we have a solid particle having a size of 0.12 millimeter and the shape factor or sphericity factor of 0.88. And the solid particle also have a density of 1000 kilogram per cubic meter. And this solid particle are to be fluidized using air at 280 m absolute and 25 degrees Celsius. And we know that the voidage at minimum fluidizing conditions, or EM or epsilon MF, is 0.4. Now, if the cross-sectional area of the empty bed, so if the cross-sectional area of the bed is 0.3 square meter, 0.3 square meter, and the bed contains 300 kilograms of solid, calculate the minimum height of the fluidized bed. Okay, so we go to point A first. So we know that the volume of solid is, we do not know the volume of solid is. What is the volume of the solid? But we know the mass of the solid. It's 300 kilogram. But we know Also, aside from the mass, we also know the density of the solid particles. So we can find the volume of the solid, yeah, by dividing the mass of the solid with the density of the solid, yeah. So we know that the volume of the solid is 0.3 cubic meter, yeah. Nah, and then the height of the solid, yeah, would occupy in the bed, right? Of course, yeah. Now, if the epsilon 1 equals to 0, miss, why 0? Yeah, so let's say we assume that there is no void at all in the bed at first. At first, assume that there is no void at all in the bed. Okay, so of course the epsilon 1 equals to 0 because there is no void. Yeah, and what is the L? Yeah, what is the length when the void is 0? Yeah, nah, let's say it's pejal. Yeah, let's say it's the solid has no void atau pejal. Yeah, so of course after we find the solid, after we find the volume of the solid, which is 0.3, yeah, we can just directly divide the volume of the solid with the cross-sectional area of the bed. Yeah, because we assume that there is no void, right? So of course the total volume, yeah, of the solid, yeah, divided by the cross-sectional area of the bed equals to the length of the solid itself. Yeah, so it's 0.3 divided by 0.3 cross-sectional area equals to 1 meter. Yeah, so when there is no void, when we assume there is no void in the bed, ya, so kita menganggapnya itu pejal, maka volume dari solid particle kita bisa langsung bagi dengan cross-sectional area dari bed itu sendiri, sehingga kita bisa dapetin tinggi dari bed, which is 1 meter. Yeah, so this is L1 and this is epsilon 1. Okay, and then using the equations above, I think it's 3,131, I think. Let me try to check. Oh, sorry, 3,130. This, yeah, by using this, yeah. Okay, wait. Nah, okay. Nah, by using this, I will fill L1 and epsilon 1 here. And in the equations above, it is L2, right? And this is epsilon 2. Yeah, but since the second condition is at minimum fluidization, yeah, so I will change the notation of 2 becomes MF. Yeah, the notation of 2 here become MF. Okay, because what I want to know, what I want to find here is the minimum height of the fluidized bed. Okay, so the minimum height. So the height of the bed at minimum fluidization. Yeah. So the second condition is at minimum fluidization. So that's why I changed the notations to become MF. Okay, I know that the epsilon MF, yeah, is 0.42. I will change it. I will fill it here. I will substitute it here. So I can find the LMF. It is 1.724 meter. Yeah. Okay. So I will go to question B. Calculate the pressure drop at minimum fluidizing condition. So delta P at minimum fluidization. Okay. So I know that we want to make the solid particle moves by using air at 2 atm at 25 degrees Celsius. And by using the appendix A3, I found that the viscosity and density of the air is this one. Yeah. So 2 atm, I will change it to Pascal. It becomes this. Yeah. And then the particle, yeah, I know from the problem, it's 0.0012. And then the density of the particle is this 1000, and the sphericity factor is 0.88, and epsilon MF is 0.42. So I will use the equations 3.131. Yes, this. Oh, sorry, I will use this Yeah. I will use this 3.32. Yeah. I will use 3.32. Yeah. Okay. And by substituting all the value, yeah, I can get the pressure drop. Okay. So that's 4.B. Yeah, I used 3.132. Okay. And then C, calculate the minimum velocity for fluidization. So I have to find the VMF accent. Yeah. So again, I will use this equation 3.136. 3.136. Yeah. Okay. So in 3.136, there are three terms. Yeah, there are three terms, right? And then I will fill all of the known variables, yeah, into the equations, and I can find the Reynolds number at minimum fluidization. Look, Miss, why should I find the NREMF? Can we just directly find the velocity MF accent? Yeah, but actually it is more easier. Yeah, when you use this, it is more easier for you to find the VMF accent. Yeah, okay, because the calculation is more simpler. Yeah, if you put this here, actually it can. Yeah, you can directly find VMF accent. Yeah, but again, you have to fill dp rho mu, right? So they use this. After you find the NREMF, then we can just substitute all of this, yeah, the known variables, leaving only VMF accent, and we can find VMF. Yeah, actually you can. Yeah, so just substitute these equations to this. Yeah, but then again, yeah, you have to fill dp, you have to fill density, you have to fill mu. Yeah, in all these two terms. Yeah, so it's a little bit more confusing and complicated. Yeah, if you use an NREMF, you fill in only less parameters that you have to fill in this equation, in this long equation. Yeah, and after you find NREMF, then you can just use one equations to find VMF, which is this. Yeah. Now, and then for question B, yeah, we are asked to use equation 3.138 to calculate VMF accent, assuming that the data for sphericity and epsilon MF are not available. Okay, so we use equations 3.138. Yeah, so this. Yeah. Okay, so we put all the known value, then we can get NRE MF, which is 0.07129. Yeah, and then by using this equation again, yeah, and fill in all the known variables, we can get the VMF. As you can see, both give similar value. Okay. Okay, so we go to the next topic, which is the expansion of fluidized bed. Okay, as previously known, let me open the pointer first. Nah, yeah, as previously known, yeah, that higher fluid viscosity, velocity, yeah, sorry, this is not viscosity ya, teman-teman. Higher fluid velocity, yeah, leads to a higher particle distance. Yeah, because when we add more velocity, yeah, if we have a higher velocity of the fluid, it will make the particles fluidize more. So therefore, it will have a higher particle distance. And therefore, it will also result in a higher voidage or higher empty spaces. Yeah. Nah. Oh, why it can. Nah. To measure the expansion of the true fluidized bed, so not the minimum fluidization, ya teman-teman, but the true fluidized bed. So this one, yeah, which is indicated by the value of epsilon, yeah, we can use equations 3.139. Yeah. Now, but these equations 3.139 is only valid for the Reynolds number for fluidized bed less than 20 and the epsilon less than 0.8. Yeah. Okay, so I will go to the Janko, please. Nah. Okay. Yeah, so for me, so for us to find, yeah, the epsilon, yeah, the actual epsilon when the particle of packing material is fully fluidized, yeah, we can use these equations. Yeah, but this equation is restricted. Yeah, it's restricted only when the Reynolds number in the fluidized bed, yeah, is less than 20 and the epsilon is less than 0.8. Okay, yeah, so you have to pay attention, really attention into this parameter. Yeah, so yeah, okay, so only valid for NREF less than 20 and epsilon less than 0.8. Yeah, then 3.139, equation 3.139 is valid. Yeah. Okay. Now, Miss, I haven't learned about NREF. Yeah, I have learned about NRE, the common NRE. Yeah, yang BV rho per mu. Yeah, and then also I have learned about the NRE for particles. Yeah. Okay, and then NRE for packing, for packed bed. Yeah, the fluid in the packed bed. And then I have also learned about the NRE for minimum fluidization. Yeah. Okay, but this is the new NRE again. Yeah, we call it as NREF. Yeah, or Reynolds number for fluidized bed. Yeah, which calculations, yeah, can be expressed as this: dP times Vxn times rho divided by mu. Yeah, so the calculation of this must be lower than 20 and the epsilon must be lower than 0.8 for the equation 3.139 can be used. Okay. Now, the fluid flow rate, yeah, of the fluidized bed itself is constrained first, yeah, by the minimum VMF accent, yeah, and second by the entrainment of solid from the bed trap. Can you clearly explain, Miss? Nah, let's see, yeah. So the fluid flow rate of the fluidized bed, yeah, we refer it as the Vxn. Yeah, nah, let's say if the Vxn is less than the minimum VMF accent, yeah, so of course there is no fluidization, yeah, because the velocity of the fluidized bed less than the minimum fluidization. And so of course there is no fluidization. So for the bed fluidized, the velocity of the liquid, yeah, must be higher than VMF accent. However, yeah, when the Vxn or the flow rate of the velocity of the fluidized bed is higher than the terminal velocity, yeah, the particles, the solid particle will escape the bed trap. Yeah. Yeah. So let's say, yeah, if the velocity of the liquid is very fast, so of course there will be solid particles that will be overflown, yeah, and go out from the tank. Yeah, and we do not want that. Yeah. Okay, so that's why it must be lower than the terminal velocity so that it will not go out from the tank. But it also must be higher than VMF so that it will fluidize. Yeah, so that's the constraint. Yeah, so the first is minimum VMF accent, and the second is the entrainment of solid from the bed trap. Okay, now the terminal velocity, yeah, can be calculated by equations 3.140. Yeah, and this equation only valid if the Reynolds number for fluidized bed is lower than 0.4. Yeah, And you can use equations 3.141 if the Reynolds number for fluidized bed is higher than 10,000, than 1,000. So I will go to the Janko, please. Yeah. Okay. So for fine solid with the NREF less than 0.4, you can use this. Yeah. VT action over VMF action equals to 90/1. Yeah, this is only for fine particles. Yeah. While for 3.141, it's for large solid and with the NREF of higher than 1,000. VT action over VMF action equals to 9. Okay. Yeah. Okay, so we go to the example 3.17. Yeah. So by using the data from example 3.16, we are asked to estimate the maximum allowable velocity VT action. Yeah. And using an operating velocity of 3 times the minimum, estimate the voidage of the bed. Berarti yang ditanyakan adalah maximum allowable velocity, jadi VT, terminal velocity-nya. Yang ditanyakan satu. Yang kedua, kalau kita ternyata beroperasi hanya 3 kali lipat dari minimum, nah kita disuruh menentukan berapa sih epsilon dari bed itu jika menggunakan velocity operating, ya, which is 3 times the minimum. Okay. Nah, so we know from the example 3.16, yeah, we go up, yeah, the inner EMF, it's 0.07764, yeah, and then the VMF action is the 0.005029, yeah, and then the epsilon MF is 0.42, again, here, yeah, okay, nah, wait. Nah, and then we know that the NRE, yeah, the NRE is less than 0.4. Yeah, NRE is less than 0.4. Yeah, so we can use 3.140. Yeah, to find the maximum allowable velocity. Yeah, since I know the VMF is 0.005029, yeah, and the one that we want to find is the VT action. So VT action equals to 90 times VMF action. Yeah, so it's 0.4526. Okay. Okay, and then, yeah, the operating condition that we want to use, yeah, the operating velocity that we want to use is only 3 times the minimum. Yeah, so we know the minimum is 0.005, right? So 3 times of it is 0.015. Yeah. Now, to determine the epsilon at this new velocity, yeah, we can substitute into the equations of 3.139. Yeah. Okay. So can I go up? So V action equals to K1 times epsilon to the power of 3 per 1 minus epsilon, right? Nah, so for the minimum fluidization, yeah, the VMF action is this value, 0.005, right? K1 we don't know, yeah, and then but we know the EMF, yeah, so I can just put EMF to the power of 3 divided by 1 minus EMF, since this is also VMF action. Yeah. Okay, so I will go up again. Yeah, so V action equals to K1 times epsilon to the power of 3 per 1 minus epsilon. So if I change this to VMF action, I can also change this to EMF, right? Okay. Now, so by using this equation, I know the value of K1, which is 0.03938. Yeah, and by using this value of K1, yeah, I can put the V action Yeah, so the operating condition I can put as the Vxn, and then K1 I know from the previous calculations. Then I want to find this epsilon value. Okay, so this is the one that I want to look for. Yeah, so after some rearrangement and calculations, then I get the epsilon value for the operating velocity is 0.555. So that's for the minimum, that's for the voidage of the bed at the operating velocity. Now, maybe you question this, yeah? Maybe you question this, loh, Miss, why we use 3.140? Yeah, not 3.141. Yeah. Okay, let's say, oh yeah, because it's less than 0.4, it's only 0.07764, right? But this is not NREF. Yeah, this is for NREF less than 0.4. But this is NREMF. Yeah, it's not NREF. Yeah. So actually you cannot say that we can use this one. Yeah. You cannot say that. Right? Nah. Okay. Nah. So the answer is when we see this, yeah, we can actually assume, yeah, that NREF is equal to NREF first. Yeah, so assume first, yeah, that the NREMF equals to NREF. Yeah, so that you know what you have to do. Yeah, either using this or using that. Yeah. However, after you find the operating after you find the operating condition, yeah, of the velocity, yeah, so 0.01509, okay. Now, you can try to put it into this equation. Okay. Sorry. Now, you can try to put it in these equations, yeah. So dp times 0.01509 times density over mu. Okay. Now, if it's still less than 0.4, if it's still less than 0.4, then your assumption is already correct. Yeah. Okay. Yeah. So first assume, yeah, because we do not know, right? We do not know the velocity, the operating velocity yet, right? So that's why we use the NREF, yeah, as a standard, yeah, for us to choose whether we use the equation 3140 or 3141. Yeah. However, after we know the velocity of the operating velocity, yeah, which is 0.01509, then we can try, yeah, to check. Yeah, we have to try to check, yeah, by using the NREF equation. Yeah. And if it's still less than 0.4, then your assumption is correct. So the calculation by using 3140 is correct. Yeah. Okay. So I will go again to the next slide. Yeah. Nah, which is the last subsection, yeah, in this chapter, in the subchapter, yeah, which is the minimum bubbling velocity. Yeah. So the minimum bubbling velocity is a velocity at which bubble first observed. Ya. Jadi kecepatan di mana pertama kali bubble itu terlihat. Oke. Nah, Mbak Isa. Nah, there are two groups of particles. Yeah. Group A is a particles that tends to exhibit particulate or smooth fluidization. Yeah. So it is difficult for them to form a bubbling fluidization. Yeah. And group B is a type of particles that tends to exhibit bubbling fluidization. So it's easy for them to create a bubble, yeah, to create a bubbling fluidization. Yeah. Now, for group A, yeah, usually the VMB stands for velocity of minimum bubbling. Yeah. Okay. VMF is velocity for minimum fluidization. Yeah. So for group A, since I said to you, it is easy for them to create a smooth fluidization, but it is difficult for them to create bubbles. Yeah. So for group A, yeah, the velocity, the minimum bubbling velocity will be very much higher than its minimum fluidization velocity. Now, while for group B, the velocity for minimum bubbling, yeah, you can say it's a little bit the same, yeah, a little bit equal to the minimum fluidization velocity. Yeah, because as I said to you, for group B, it tends to exhibit bubbling fluidization. So it's easy for them to create bubbles. Yeah. So at the minimum fluidizations, they already start to bubble. Yeah, but for group A, since it's difficult for them to create bubbles, yeah, so the minimum bubbling velocity of those particle in group A is very much higher than its minimum fluidization velocity. Yeah. Now to calculate the minimum bubbling velocity, yeah, you can use equation 3.142. Yeah. Now, if the velocity of the minimum fluidization is larger than the velocity of the minimum bubbling, yeah, so use the velocity of minimum fluidization as the minimum bubbling velocity. Ya, jadi kalau minimum bubbling velocity Anda itu lebih kecil daripada minimum fluidization velocity Anda, pakai minimum fluidization velocity Anda itu sebagai minimum bubbling velocity. Karena tidak mungkin, ya, tidak masuk akal, ya, jika bubbling terbentuk sebelum adanya fluidizing. Ya, okay. Yeah, and then you can read by yourself example 3.18, yeah, because it's easy, okay, and also short. Yeah, okay, so if you have any question, yeah, you can drop a message by using WhatsApp, or you can also drop a message in the comment section below. Yeah, and there will be assignment for you, yeah, to work on, which is 3.112 and 3.114 from John Coplis. Yeah, and please submit it, yeah, before April 17, yeah, which is on Saturday at 9 a.m. sharp. Okay, thank you very much, and see you next week. Bye-bye.